We calculated the potential function at a point P, which was, remember, the difference between P and infinity, if we had a ring of charge Q. And now let's consider this to be a positive charge. And we found that the potential function for this ring, and that's the difference between the ring and infinity, so that's V of P. Infinity we chose to be 0, was equal to KQ over Z squared plus R squared to the 1/2. Now, let's imagine that we place a charge Q right there, and we release Q, and we want to make sure that we can see this. So we release Q from rest. And our charge Q will be negative. Well, we expect that Q will be attracted by the ring. And what we'd like to do is calculate, we want to find the speed, VQ, of the ring when Z equals 0, because we expect this charge to move down there. Now, what we'll use is our energy theorem that will say that 0 equals delta K plus delta U. And we're not putting any external work into this system. Now, delta U, we know, is the change in potential. So what we've described here is we're starting the particle at, we're going to end at the origin, and we're starting the particle at Z. So we start the particle at a distance Z away from the origin, and we're asking, what is the change in potential energy of this particle till it gets to the origin? So that's what we mean in this problem by Q delta V. And so what we have is 0. Well, we have the kinetic energy of the particle. Let's say it's mass m. And it's going at some speed, VQ squared, when it gets to the origin. That's its final kinetic energy. It was released from rest. That's its initial kinetic energy. And now let's write down these two functions for our potential. So this point P was a distance Z away from the axis. So what we're looking at is, what is this function when Z is 0? Well, that's simply KQ over R. So our first term is KQ over R. And the second term is where the function, where the particle potential, where it started. So that's KQ over Z squared plus R squared to the 1/2. And so what we have here is that we'd expect that our particle will now have a solve for the velocity, and we get VQ. So what I'm going to do is I'm going to bring this term over to the other side, and I get KQ over Z squared plus R squared to the 1/2 minus KQ little q over R. The whole thing is multiplied by a 2 over m. And we're just taking the square root of this entire quantity. And I can simplify that to be square root of 2 over m. Let's pull out all the common terms, and I get 1 over Z squared plus R squared to the 1/2 minus 1 over R. Now let's check our result and make sure that we have the right calculation. So the first thing is, let's look at this term in here. Clearly, the denominator here is larger than this, so this quantity is negative. How can I have a square root of a negative number? Well, remember that these two charges are opposite, and the factor, these two quantities, is less than 0, so I have two negative signs, giving me an overall positive quantity in the denominator, and so that is what the velocity of the particle is when it reaches the origin. So we've used our concept of potential difference function to be able to apply it in the energy principle to calculate the speed of this charge when it gets to the origin in the presence of this source, when it was released from rest a distance z above the ring.